All right, I want to talk about how the derivative affects the shape of the graph. All right, so I'm going to talk first about the first and second derivative test. So first derivative test and then the second derivative test. We'll talk about it all at once here. So what I want to do is I want to graph the, let's just look at a simple graph of a function. And let's make it green. All right, so if you look, the slope of the graph is 0, maybe like right there, and then it's 0, maybe like right there. So let's call that A and then that B. Slope of the graph is 0, so M is 0 there, and M is 0 here. All right, now before A, the slope is positive, and after A, the slope is negative, and then after B, the slope is positive. So around A and B, if you look at this on a number line around A and B, the slope is positive and then it's negative and then it's positive. So we call these the intervals of increase and decrease. So what I want you to notice also is that there's something called the concavity here. So if you look at this part right here and then the part right here, the concavity is different. So it looks like it's concave down here and then up here. Now, if you look, the local maximum at A, so A is a local max, right? So we have a local max here at A, and then a local min at B, local min at B. The max at the local max is where it's concave down, and where it's concave up, that's a local minimum, usually, okay? So the second derivative test, so this is the first derivative that we had here, the first derivative test. The second derivative test will tell us the concavity up and down. So let's see, so f double prime will tell us the concavity. And so when you do the second derivative, we're going to talk about how to determine the intervals of concavity and what are called the inflection point. So the inflection point is where it changes concavity. It goes from concave up to concave down. And that would be maybe somewhere in here. We'll call that C for a second. So what I want you to notice about that is the following. Let me erase some of this. Is that if you look at the slopes of the derivative of the function, the slopes of the function, they're positive and then they're negative here. And then they're negative here, just like I said before, positive here. But around the inflection point, the first derivative is going to change in a sense. And so we'll get to that in a second. So let me show you a problem and we will analyze that a little bit. Okay, so I want to do number 10 here. So let's write it down. So f of x is, so the first thing you do is you take the derivative. So you take the derivative, you get 6x squared minus 18x plus 12. You set that to 0 to find the critical numbers. So we're finding the criticals. All right, so critical numbers. You can take out a 6 automatically, just divide by it, because it's set equal to 0. So 3x plus 2 equals 0. And so the 6 we don't really need to worry about. We're just going to, let's just divide by it. So we get x squared minus 3x plus 2 equals 0. And then the 6 will not affect what the critical numbers are, okay? It will affect the other things about the graph, but not the critical numbers. And that's really all we're looking for right here. So it's x minus 2x minus 1 equals 0. So the criticals are x equals 2 and 1. All right, so I'm going to go ahead and take the second derivative, f double prime of x. And let's see what we get with that. So I'm going to take it and I'm going to use this one for the second derivative. So that's 12x minus 18. I'm going to set that to 0 as well. So 12x equals 18. So that would be x equals 18 over 12, or to go, that would be 3 over 2. We would have gotten the same thing if we would have just taken the derivative here of the first derivative. If you take out the 6, it would be 2x minus 3 equals 0, and then you'd get 3 halves as well. All right, so this right here we're going to use, and these two right here we're going to use. I'm going to show you where these are used in just a second. So the first thing I do is I'm going to do the what's called the first derivative test. And what you do is you take your critical numbers and you put them on a number line. So I'm going to take my 1 and my 2, and I'm going to put them on a number line, 1 and 2. And I'm going to find test points in between them. So I'm going to use maybe 3/2 here. It doesn't have anything to do with this 3/2 here. I mean, it's the same number, but I'm just using a test point in between each interval, or in each interval. After 2, I could use 3, and after 1, I could use 0. So what I'm going to do is I'm going to plug these into the first derivative. Now I can plug it into this one that has a 6 on it, or without the 6, and I just want to see what the sign of the function is. All right, so the sign of the function is 0. The sign of the slope, excuse me, the sign of the slope of the function. And it's 0 there because the first derivative that's how I got 1 and 2. That's how I got 1 and 2 to begin with, was setting the first derivative equal to 0. So up here on top, this will be the sign of f prime. F prime. So I am going to plug in 0 into this one here if you want. And when I do that, I get a positive number, so that's a positive there. I'm going to plug in 3/2. Now I can plug it in there, or in here, or I can plug it into this right here, which is the factored form of it. The 6 was taken off, but that's always just positive, so it doesn't really affect the sign of the first derivative because it's positive. So if I plug in 3/2 in there, so 3/2 minus 2 times 3/2 minus 1 minus 1, I'm going to get a negative here and a positive here. So when you multiply negative times a positive, you get a negative. And now I'm going to plug in 3, and I'm going to go ahead and plug it in this as well. So I get a positive and a positive. That gives me a positive. Multiply them together, you get a positive. If that's confusing you, just plug 3 into the original, to the first derivative. Just plug it into this right here, and you'll get a positive number. Now, what this says is that the graph, remember, this is the sign of the derivative. So if the derivative is positive, the slope is positive. And then the slope is negative, is 0. I'm just looking at these signs right here. All right. So then it's 0. So it's going to even out. And then it's negative, and then it's 0, and it's positive again. So it's positive, then it's 0, then it's negative, then it's 0, then it's positive. This is just the sign of the derivative. I don't know where these things are yet. I don't know where the x and y axis are. I can find out right now though. So why don't we check that out? So now what I want to do is I want to plug in the critical numbers, these two, into the function itself and see what I get. So the function was 2x cubed minus 9x squared. So I do f of, when I plug in 1, I get 2. And when I plug in 2, I get 1. Now, it's just a total coincidence that when I plugged in 1, I got 2, and then when I plugged in 2, I got 1. That almost never happens like that. So don't think that that's how you do it. So what I want to do now is I want to graph this thing. So I'm just going to start sketching it. Okay. So at 1, we get the value of 2. So 1, we get the value of 2. So it's here. And then at 2, we get the value of 1. So 2, this is not to scale. We get the value of 1. So it does that. And then somewhere in the middle, 3/2, there's something going on there. All right. So there's 3/2 right there. All right. So the web assignment is going to ask you what the intervals of increase and decrease are. Where the first derivative, so when f is increasing, this means, let me write that a little better. When f is increasing, this means that f prime is positive. So let me write this down, greater than 0. When f is decreasing, this means that f prime is negative. All right. think about it. When the function's going up, the slope is positive there. When it's going down, the slope is negative there. All right, so so there's that. Now, what I want to do with this is I want to take this and I want to use this with the second derivative now. So now I'm going to say when f prime is increasing, this means that the second derivative is greater than 0. And when f prime is decreasing, this implies that the second derivative is less than 0. All I've done is I've taken the derivative of each of these f's and applied it there, because f prime is a function itself. So it'll increase and it'll decrease. So I'm just applying the same rule to f prime as I did to f. So why am I talking about this? Well, now I want to take the second derivative and see what's going on there. So I'll take the second derivative of the function. Oh, well, we already did that there. So now what I want to do is I want to do what's called the second derivative test. All right, so second derivative test. And that'll be another sign chart. Well, this is a sign chart for the second derivative. Second derivative test is something else, but let's just do this anyway. So we got 3/2. That's what I got when I took the second derivative. I got when I set it equal to 0. So I got 3/2, and now I'm going to do a sign chart for that. So a number on the left of 3/2 is 0, and a number on the right of 3/2 is 1.5. Let's just say it's 3. Okay, so I'm going to plug those numbers into the second derivative. So this is the second derivative here. So when I plug in 0, I get negative 18. I get the negative there. When I plug in 3, I get 36 minus 18. That will be a positive number. The second derivative is 0 at 3/2. So what this says is that before 0, the second derivative is negative, and after 0, I'm sorry, 3/2. Before 3/2, the second derivative is negative, and after 3/2, the second derivative is positive. So what does this mean for the first derivative? Well, that means the first derivative is, let's see, what was the rule? When it's increasing, the first derivative is increasing, the second derivative is positive. So this means that f prime is increasing here, and f prime is decreasing here, where the second derivative is negative. All right, so what does that mean for the graph? Let's just graph this thing. What's the intercept? Well, the y-intercept is 3, because when you plug in 0 for x into the original function, you get, I'm sorry, negative 3. Negative 3. All right, and so, and we can find the, we're going to find the x-intercepts in just a second. So I know it goes like this, and then down, and then up like this. Okay, so this is way down at negative 3. This is not to scale. Now, how do I know that it doesn't like come back down again? Well, because the first derivative only gave us 2 points. And if it only gives us 2 points, critical numbers, it doesn't like come back down again, all right? So if you notice, it's concave down here, and it's concave up here. So let's check out, if you look, 3/2 is right between those. So concave down means, sorry, the first derivative values are increasing. So when it's concave down, they're decreasing, and when it's concave up, they're increasing. So if you look, let me draw the graph a little better. Say it would look like this. So the first derivative here, we're talking about the first derivative, positive, 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 0, negative, 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 0, positive, 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 positive. So what's happening is it's positive, and then it's going to 0, and then it's negative, and then at some point it's negative, and then it goes to 0, and then it's positive. So the first derivative, you could graph right below it as it's positive, and then it's 0, and it's negative, comes up to 0, and it's positive again. Positive, 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 0. This is the first derivative. And then it's negative, 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 negative. its own graph, okay, and then 0, and then it's positive, 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 all the way up. So don't get the first derivative. This is the function f, and then in purple is the first derivative. So decreasing, it's decreasing here, and it's increasing here. And so where it's concave down, the first derivative is decreasing. And where it's concave, where the original function's concave up, the first derivative is increasing. All right, and so these are called the intervals of concavity. And so if we go back to the second derivative, then we say it's concave down where it's negative, where the second derivative is negative, and it's concave up. So concave up and concave down, like that. That's what we say. All right, so there's a nice little test. It's called, this is actually the second derivative test, what I want to talk about now. This is, I'll use a different color. What you can do is you can use the second derivative, f double prime, to see if criticals are max or min, So the critical numbers were 1 and 2. So I'm going to plug those into the second derivative. So where was the second derivative? It was 12x minus 18. Yes. So f double prime is 12x minus 18. So I'm going to plug in 1 into that, and I get 12 minus 18 is negative 6, which is less than 0. All right, now plug in 2. Negative f double prime of 2 is 24 minus 18, which is 6, which is greater than 0. So notice how it changes sign. It's different signs. So it turns out that if the second derivative, if you plug in the critical number into the second derivative and you get less than 0, all right, that means that that is a local min. And if you get greater than 0, that'll be a local max. Why? Well, because we said that where the second derivative was negative, where the second derivative is negative, the function's concave down. Oops, these are backwards. Sorry, this is a max here. Yeah, that's right, and this is a min. I never memorize this stuff. I always have to derive it every time. It's minimum where it's concave down, it's maximum where it's concave down, and then it's a minimum where it's concave up. And if you look, that's what happened at 2. At 2, it was concave up, and so that is where the second derivative was positive. And then it was concave down at 1 here, at 1 there, where the second derivative was negative. That would be a max. So there's a lot going on here that's a lot behind the scenes. So I'll do another problem in the next video.